welcome to the fourth tutorial of FIR on ping. In this particular tutorial, we'll go over the following things. In the last tutorial or the last implementation of the last tutorial, we looked into one channel and two paths where we changed the number of paths but not the number of channel. Over here, in this particular tutorial, we'll do both, as we'll be implementing 2 channel and 4 paths and their hardware and software executions, along with the usage of a COE file or the coefficient file. I will tell you how to configure this file in order to use it for one particular coefficient set and many more coefficient set. The task is something for you to try out by yourself. In this particular tutorial, your task is to try to implement a 3-channel, 1-path FIR filter using the COE file. Before we go directly to the implementation, let me show you a diagram of how a 2-channel 4-path FIR filter looks like. By 4 path, I mean 4 data paths, i.e. 4 inputs of the same signal are being taken as input every single clock cycle. Let me explain it further. I have an FIR core which is configured to have 4 data paths or has a input capacity of 4 input samples every single clock cycle. And for the first clock cycle, it behaves like channel 1 and takes my input A1, A2, A3 and A4 and filters them. On the very second clock cycle or the very next clock cycle, the FIR core now behaves like channel 2 and takes input B1, B2, B3 and B4 and filters them. In the third cycle, it takes A5, A6, A7 and A8 into account and input and filters them, and this pattern keeps following till the end of the clock cycles. The filter we'll be using for this particular implementation remains the same, an order of 26, the number of coefficients being 27, the nature of the filter being a low pass filter and the cutoff being 80 MHz.
Let us look at the block design of tutorial 4. We start with creating the block design. We first add our zinc IP, run the block automation. In this particular tutorial, we will be implementing a 2-channel 4-path configuration. So for that, we first enable our ACP port, disable all the peripherals. Next step is to add our DMA. Now, since I have 4 paths, it means that, just a second, before this we first change our width of the buffer length register from 14 to 23. Next step is to change the memory map data width from 32 to 128. Same goes from the stream memory width. Now max burst size is turned to 256. We will now allow unaligned transfers. And the next step is to, in the right channel, we change the memory map data width from auto to manual and select 128 over here as well, along with the max burst size being 256. Next step, we add our FIR IP. Now let's configure this IP. I have let's use a coefficient file. I already have a coefficient file over here. Let's go to our tutorial 4. We already have a coefficient file over here. This coefficient file looks something like this. It contains a low pass filter with cutoff of 80 MHz. Next, we as you can see that The number of coefficient sets is by default 1, which is what we require. And the Vivado has sensed I have 27 coefficients, or we have uploaded 27 coefficients in the COF file. The COF file looks something exactly like this. We start off first with defining a radix. Radix defines the base of the number or the representation we have used. In case I turn this to 16, it will think of all of these coefficients as in hexadecimal. Over here I am keeping it 10. Next step is to use a keyword called data. Use an equal to sign and use all of the and copy paste all of your coefficients from the MATLAB onto the coefficient file, while making sure each of these coefficients is divided by a comma over here, as you can see, and at the end of it you apply a semicolon both after radix and after coef data. Please use the exact keywords radix and coef data to ensure there are no errors. Next step, we use the filter type single rate. We move on to channel specification, where our channel sequence remains basic. The number of channel goes to 2 and the number of path goes to 4 with an input sampling frequency of 100. We next go to our implementation tab and change our input data width to 32, and on the interface tab we select packet farming and enable output T ready along with enabling a reset N. Next we run connection automation. After this connection automation, let us look at the input and output bits of the FIR and the DMA. Let us look at the input first. I have 128 bits over here, and same goes for the FIR compiler. Since we have the same number of bits, we can directly connect the interface. Let us connect a reset N and a clock after this. Now let us look at the master interface of the FIR compiler and the DMA. As you can see over here that I have 192 bits on the master interface but only 32 over here. So we will use a slice again. In the very first slice, our D in input will be 192. As you can see, it is 192 over here, so we will use 192 over here. Next we go from 31 is to 0 or 30, and our D output width will be 32, and connect this to the M axis T data. Next we control and placed another slice. Now we go from 79 to 48, I believe. The trick is to take 31 and add 16 signals. Take 32 and add 16 signals to it, which we receive is 48. So we start from 48 and add 32 bits, which gives us and add 31 bits to this. 48 plus 31 is 79, so we have received 79. Next we connect this to the M axis T data 2. Next we again copy paste this slice to get a second slice, where to the 79 we add 16. Let me just check. Yes, my apologies. We start with our D in input being 192, then to 79 we add 17 and get 96, so we get 96 over here, and then to 48, sorry for the delay, I have come back now with the proper calculations. In the first slice, I go from 0 to 31 bits with a total of 32 bits as output. Then in the second slice, I go from 48 to 79. Why so? Well, I have 16 signals as excess signals that can be ignored, and so to 31 I add 16, which gives me, I add 17 as I am using a zero based numbers. So 31 plus 17 would give me 48, which is where my next number starts from, and to 48 I will add 31 to give an output of 32. Thus I will write 79 over here. Similarly, on slice 3, I will add 16 to my 79, which gives me 17 to my 79, which gives me a 96, and then 31 further to receive 127 and an output width of 32. And finally, in the third slice, I start with 148 from 174 to 143 bits and a D out of 32 bits. I will connect all of these with the M axis data T data, and the next step is to concat all of these slices. Over here I will change my number of ports from 2 to 4, and the width of all of these to 32. Next step is to connect all of these slices to the appropriate concat port. 0 to 0, 1 slice 1 to input 1, slice 2 to input 2, slice 3 to input 3, and as you can see, my concat now gives me perfectly 128 bits. Next step, we use a stream width converter. Why a width converter? Well, my DMA can still only accept 32 bits while I have 128. Now, since 128 by 8 gives me 16 bytes, I will change my interface to 16 bytes and the master interface to 4. I will next enable TLast and connect the T data as access T data, or the slave interface that accepts data of 128 bits, to the concat IP. Next step, I will connect the M access data TLast to the TLast of the width converter. Similarly, the T-ready from the FIR compiler to the T-ready of the width converter, and so on for T-valid. Next, I will connect the A clock and the A reset. After the A reset, you will see that I have 32 bits over here and 32 over here, and since the bits are same, so I can directly connect the interface. Next step is to regenerate the layout and validate our design. As you can see, our validation is successful. There are no errors. We can go ahead and start generating our output products. Once the generation of output products is done, we will create an HDL wrapper. Once the HDL wrapper generation is done, we will generate a bit stream. As you can see, my synthesis and implementation are queued. Once these are done, my bit stream generation will start. Look at the code for tutorial 4. We again start with importing all of our filters and doing the overlay and loading the bitstream onto the FPGA. Then we start with our usual sampling parameters, which is sampling frequency being 200 MHz, the time total duration of the signal being 2 into 10 raised to 5 seconds. The number of samples being generated are 4000 over here and are stored in a time vector t over here. Next, instead of generating one test signal, we generate two test signals, as we have to filter out two channels. On the first channel, we have a signal A, which consists of two frequencies 10 and 90 MHz, while channel 2 has to filter out signal B, which has again two frequencies 30 and 80 MHz. We first start with the software executions. We first define our coefficients, use the L filter to do the filtering for time domain convolution, and figure out the time required for the convolution of two signals. Then we move on to the frequency domain multiplication, where we pad our coefficients by first creating a zero array and then adding the coefficients. Then we start our timer and then multiply both of these both coefficient and samples in frequency domain, and then turn them back into time domain. This calculates the timings required, or the timings taken to execute both of these commands, which is A frequency and B frequency. Next step is the hardware execution of a 2-channel 4-path. This is where TDM or time division multiplexing comes into account, where we have to interleave our input before giving it to the hardware. We first create an array called input data 8 times the size of our n, where on the first or the 0th position we keep a sample from signal A, and this is path 1. Then on the first place comes the sample from signal B. This is also path 1. For the second channel, this is path 1 for channel 0, and this is path 1 for channel 1. Similarly, this is path 2 for channel 0. This is again path 2 for channel 1. Similarly, we go down till path 3 for channel 0. Then we have path 3 again for channel 1. Then we have path 4 for channel 0. And finally path 4 for channel 1. This is how the interleaved input is given. Next, we allocate memories for the input output buffer and copy the data from input data onto input buffer, after which our timing for hardware execution starts and it is given to the DMA, and we are supposed to wait for all the executions to complete before ending our time over here. Next, we print our hardware execution time. After printing this, now we can't just print our output buffer. We first have to de-interleave our outputs and then plot them. So on the as you can see over here, I have my sample for signal A is on elements 0, 2, 4 and 6. Similarly, this is done 0, 2, 4, 6 are combined. Outputs of all of these 4 elements repeatedly are combined, and at every odd position, which is 1, 3, 5 and 7, is combined to create an output for channel B or signal B. Next we do the the fast Fourier transform to bring all of these outputs into the frequency domain, and next we plot all of these. So currently the test signals are of 10 and 90 megahertz and 30 and 80 megahertz. According to the theory, we know the 10 and the 30 megahertz should be allowed to pass, while 90 and 80 should be attenuated. Let us look at the graphs. Our input over here, as you can see, is 10 and 90 megahertz given over here. I believe that is correct. 10 and 90 over here. Correspondingly, we have the 4 peaks, one at plus 10, one at minus 10, one at plus 90 and one at minus 90. Next we have peaks at 30 and 80. All the 4 peaks are present in input A and input B. Next we have the time domain convolution of A and B. As you can see, the 2 peaks present over here are minus 10 and plus 10, while the 90 over here was attenuated. In input B, 80 was supposed to be attenuated, which is exactly what happened. In terms of frequency domain convolution, 10 was again preserved. Over here 30 was preserved, while 90 and 80 were attenuated. The hardware output follows the same exact rule, that 10 is preserved in case of signal A, while 30 is preserved in terms of output B, while 90 in case of signal A and 80 in terms of signal B were attenuated. But as you can see, 90 was completely attenuated, while 80 has some bit of attenuation left. This is due to the fact that the LPF that we have created has a cutoff of 80 megahertz. Now moving on to the execution times. The execution time required for time domain convolution for 2 signals was 0.007 seconds, while the frequency domain multiplication was 0.017 seconds, while the hardware execution time was only 0.002 seconds. So as you can see, when we compare these, the lowest time for software execution, which is the convolution or time domain convolution, the hardware was still 3 times faster than the software over here.